So we are going to start chapter 8, right? And chapter 7 is part of chapter 8. We are going to talk about it, so going to be included in here. And then if you look at the progression of our class is that we started with, continuous function to approximate solution using method weighted residual, and then we introduced the method weighted residual using finite solution technique, and one-dimensional problem and two-dimensional problem, but still single degree of freedom per node, right? Now we are going to talk about more than 1 degree of freedom per node, one-dimensional problem, two-dimensional problem, etc. That's what we are going to work on it. So chapter 8 is a beam and frame structure. So we are going to start with so-called Euler-Bernoulli beam bending problem. And I believe everybody knows the difference between frame and truss structure. Right? What's the difference between frame and truss structure? No? You guys took statics some point, right? So truss structure is the simplest structure, which only what? Consists of two force members. Two force member means that member is going to be carry the load along the member direction, no bending. Okay, so the truss structure is as the all pin joint, and load is only applied at the pin location. So two force member. You know what two force member means, right? The member has only two force applied when you draw free body diagram, no additional force, two force member. I'm not going to go into too much detail for that one because we don't want to waste too much time on that one. But frame is going to be other than truss, that's frame. So beam is make up the frame structure. So beam bending problem is going to be like this. Both of the differential equation. You know that, right? So I don't have to develop the beam bending equation. Am I true? Okay. If you have any question, let me know. But I believe you know beam bending equation. And of course, this is same as EI and like that. So we use comma xxxx instead of this expression. So either way, you can write that. So EI is called beam rigidity. EI is beam rigidity, and U is deflection, and Q is load intensity. In other words, if you have a beam, let's say you have a simply supported beam, then you got the load here. That's going to be Q. Okay, load intensity applied through the member. And then the boundary condition, that's the fourth order. And if you remember what we talked about the first day of our lecture, if you have a fourth order differential equation, then boundary condition is going to be up to third order, one order less than the differential equation. Yes.
In the equation up there, the EI, and it seems to be, I just can't see the letters.
EI.
And then to the right, where it says like D
Q
in the middle.
here. This one?
Yeah.
U. Same as this one. So boundary conditions up to the third order, since this is the fourth order, third order, derivative, then what are that? U is deflection of transverse displacement of beam, and U comma x du dx is slope of the beam, and second derivative, okay, second derivative multiplied by EI is going to be a moment. So second derivative related to bending moment, and third derivative again relate to shear force, and EI is we call again beam rigidity. How stiff the beam is EI. E is elastic modulus. I is going to be second moment inertia of the cross section, EI, right? So those are possible boundary conditions. And in general, in here, then first two we call essential, and the other two is going to be natural. Or this is the geometric boundary condition. That's the loading boundary condition, or force and moment boundary condition, like that. Then the fourth order differential equation, I need 4 boundary conditions to solve that exactly. So if you have a simple support means we usually indicate this triangular and circle. That means this is fixed both x and y direction. This is only fixed in the y direction, but not the x direction. So to make this one is going to be statically determinate. If you fix both of them, then it becomes statically indeterminate. So to make it a little simplified, so simple support is going to be fixed xy direction, fixed y direction only. So in that case, anyhow, u is going to be 0, no deflection. We are talking about the vertical deflection, and we don't care about x right now because we don't have any force in the x direction, horizontal direction. So displacement is 0, deflection is 0, and it is free to rotate. Simple support means like this. More in a precise sense, it's going to be like that. You got a pin joint. So it's free to rotate. That means your moment is going to be 0. Second derivative is going to be 0. That's the bound function. If you have a clamp means like fixed here. If you have a clamp, then deflection have to be 0, and also slope have to be 0 here. The slope have to be 0. That's the bound condition. And then if you have a free, like this, free end, then free means that there's no force and no moment. So third derivative equals 0, and second derivative equals 0. So those are typical bound conditions for beam bending problem. Okay, and if you need any question for beam bending, then please refer to your mechanics material books, or if you have further questions, then you may stop by or contact me, then I can give you a little more extra information about that beam bending formulation. So right now our focus is that once you have your differential equation, then how can you solve that using the finite element solution technique? That is our focus. Okay, how to solve this fourth order differential equation using the finite element solution technique. Okay, so we are going to use same procedure. Okay, in other words, we are going to use also method weight residual. That means your residual multiplied by test function and integration from the domain 0 to L at its length of the beam equals 0. That's going to be method with weight residual. But if you look at that in Galerkin's technique, W is test function and U is trial function, and we use same function for test and trial. But if you see that this requires fourth order derivative, this requires 0 derivative. So there are mismatch of the requirement. This is going to be, we have a very strong requirement of because of that one. So this so-called strong formulation. So we want to have a weak formulation, and weak formulation is nothing but integration by part, right? Mathematically integration by part. So you have to carry out integration by part for that one. This one we don't have to do anything. W times Q. Q should be known value. So that carry out, all the time as it is. So nothing we don't have to worry about. But this one, we have to apply integration part. So if you apply integration part, for that one, then you got this one and that, right? So this is integration by part of this one. So WEI now, U fourth derivative becomes third derivative, and then now W is going to be the first order derivative and that becomes pseudo derivative. So that's integration by part. Anybody has problem seeing that one? Then let me know. Okay, so if you see that, then this is the boundary integral between x equals 0 and x equals L. So it's going to be just 1 point, you know, and left and right the integral. So we don't have to worry about right now. But this is the domain integral. But if you look at this domain integral, look at that. That's also test function require first order derivative. That requires third order derivative. Still imbalance between the two. This is going to dictate the, you know, the choice of the test function or trial function in Galerkin's technique. So what do you do? You apply this, apply to this one, the integration by part one more time. Then this one becomes this. Minus sign become minus, minus become positive. So this becomes this. So we apply integration by part twice. Then what you end up, again, those are the integral at the boundary, so that become boundary condition later. So if you look at that, second order, second order. So now I have balance between test function and trial function. You got it? If you apply integration by part one more time, what are you going to see? Then your test function is going to be third order derivative. Your trial function is going to be first order derivative. Then now you go another imbalance between test and trial function. So you stopped here because you got exactly equal, you know, derivative for the test and trial function. So again, in summary, nothing but here is we apply integration by part twice because 0 false, so that applying twice, so that now second and second. That's it. Any question?
What was the point under the reformulation on this again?
So you got the minimum requirement for the test and trial function. You have a higher order derivative means that you have more stronger requirement of the test function or trial function, right? So minimize the order of derivative, then you are going to make it weaker and weaker in terms of requirement of the trial and shape function.
When you say weaker, what does that mean?
So here, for example, if this is the fourth order, then if you pick quadratic function, cubic function, does not make any sense because derivative is going to be 0, right? Correct? But this one, second order derivative, so you can use even quadratic function.
Make
Right?
it simpler.
So you can pick, you know, much simpler function in a simple sense. Of course, mathematically have to be a little more elegant, but just give you quick, you know, sense of that. And so we have much simpler shape function can be picked using the weak formulation. Okay. And also another beauty in here, if you replace test by trial function and trial function by test function, then they are not equal to each other. In other words, WU or UW, they are different function. But in here, W replaced by U replaced by W, they are exactly same. So in other words, you produce a symmetric matrix too. That's another byproduct of the reformulation. Okay, so if you do that one, then if I rewrite that, it's going to be like this one. Same thing as before, except that now this domain integral is going to be divided into element level and then summation from first element to number of elements. And those are going to be the boundary term. We are going to talk about it. So you have to evaluate this one and that one, okay, each element level, and construct a matrix or column vector, and then assemble them into the system matrix and column vector. And especially this one, again, I mentioned that multiple times, that in the single term, if you have a test and trial function, this will become a matrix. And here, you only have a test function, no trial function. Q is going to be given function, not the trial function. Then this become a column vector. So this will give you a matrix, this will be a column vector. Those are going to be the boundary condition at x equals 0 and L. You see the point in the formulation? Then I have to interpolate that one. I have to interpolate that one. Then let's look at the beam. If I have a beam, let's say simply supported beam, and I apply load this one, then what kind of deformation do you expect? Of course, exaggerate. Deformation mostly very small, so we cannot see with naked eyes in most problem, but exaggerate, then its deformation looks like this. That's what you expect, right? Then this beam. Now, if I have a string, so fixed both ends string, and I apply force, what kind of deformation do you expect? Same thing like that?
Be more short, like a V.
Like this, right? Right? So what is the difference? What is the difference between the two?
The string is the piecewise function. You know, the other ones I talk about.
All right. Or more precisely, the difference is here, slope is not continuous. Deflection is continuous, but slope is not continuous, right? Correct? This one, not only deflection, but slope is continuous throughout the whole deflection. Correct? That's the clear difference. Then mathematically, if you look at mathematical equation, this is, as you already saw in our slide, fourth order differential equation, right? This one, you haven't seen it, but this is going to be second order differential equation, right? So when you develop the second order differential equation in chapter 2, we use piecewise function like that one, right? So second order, differential equation, that is proper. Then fourth order, I cannot use this kind of function because then I cannot maintain continuity of the slope. So how do I make sure the continuity of the slope, not only deflection and continuity of slope at different elements? In other words, if I divide it into number of elements at each, the nodal point here, the slope have to be continuous from one element to next element like that. How do I make sure that it's going to be continuous? To be difficult? Concept is easy. We make that as a nodal variable. In other words, you got deflection, U of V. So in that case, I use U, but U is going to be more appropriate in this notation, U1 and U2, because I use U1 and U2. But also, you have rotation, theta 1 and theta 2. So in other words, rotation itself is going to be a nodal variable. So if this is going to be nodal variable, then obviously that nodal variable share between this element and that element, so it's going to be continuous from element to next element. That ensures the continuity. Make sense? So not only deflection, but also slope are taken as nodal variable. Okay, so in other words, here, if I have a two node, again, the minimum number of nodes in beam element, but each node I have a 2 degree of freedom, deflection and slope, deflection and slope. So total 4 degree of freedom. Okay. So if you have a 4 degree of freedom, then obviously the minimum order of polynomial to interpolate this one uniquely is going to be cubic polynomial. Right? Cubic polynomial. So if you write this one in terms of this way, standard way we have done it, this is that. Then to develop shape function, we follow exactly the same procedure, except that now we have to talk about derivative. What is derivative? I mean slope. Slope is derivative. This is theta. Theta is equal to du dx. So if you take a derivative of that, it's going to be this is 0, c1 plus 2, c2 x plus 3, c3 x squared. So now at x equals 0, if you plug that, then u is going to be c0, 0, that should be u1. You know, when you evaluate this one, x equals 0. But if you evaluate this one, x equals 0, that means this is going to be c0 is 0 and 1 and then 0, 0. That's going to be theta 1. Okay. And evaluate this one at x equals L. So plugging LL. So L square, L cube. That's going to be nodal variable at U2. And plugging here L. So 0, 1, 2, L, 3 L square. That's going to be theta 2. Again, solving for this, U1 theta 1, U2 theta 2 by inverting this one. And then substituting to here, C1, C2, C3, C3 for here. Then you got the shape function looks like this. And then the shape function is given in this way. Okay, H1, H2, H3, H4, which is going to be a cubic polynomial shape function. So the procedure is exactly the same, except that now we have extra variable, du dx, which is theta. So you have to evaluate the du dx at node 1 and node 2. Right? So this is the shape function. And this shape function is different from if you use cubic polynomial and then one-dimensional problem again, 0 to L. But if I use this 4 node and use cubic polynomial, a0 plus a1x plus a2x squared plus a3x cubed, if I use same kind of cubic polynomial for this one, okay, then the shape function of this one is not going to be same as this shape function. Okay, in here you got u1, u2, u3, and u4. So that's the shape function you are going to get. And right now, what you get is going to be u1 and theta 1 at this point, and here u2 and theta 2 at that one. So totally different kind of shape function, right? Even both of them are cubic polynomial. So the traditional shape function we talk about, like this one, is only continuous of the function, but not the derivative. So we call C0 shape function, means that continuity up to the function, not derivative. So 0 means that function is, so C0 shape function. And the shape function for that one, not only function, but also slope. First slope is the first order. So this shape function we call C1 shape function, superscript 1. So C1 shape function, C0 shape function, two different type of shape function. So all the shape function we talk about is going to be C0. And now this is the first time we talk about C1 shape function. Okay. That how this is different from C0. For example, in here, if you remember, we talk about that H1 is going to be like this. This is H1. And H2 is going to be like this. H3 is going to be like this. And H4 is going to be H4. No shape function like that, huh? But for this one, the shape function looks totally different from this kind of characteristic. So, which is shown in this slide. So let's look at this one, shape function. So if you evaluate this one, H1 at x equals 0, so 1, 0, 0, 1. And if you evaluate H at L, then 1 minus 3 L squared cancel out plus 2, which is 0. Right? But also, not only function, but also we take a derivative. So let's show in here, what is H1 comma x, derivative with respect to x, which is going to be negative 6x over L squared plus 6x squared over L cubed. And H2 comma x is going to be 1 minus 4x over L plus 3x squared over L squared. And H3 comma x is 6x over L squared minus 6x squared over L cubed. And H4 comma x is now negative 2x over L plus 3x squared over L squared. Okay, so if you evaluate this one, so H1 we evaluate that. Now if you plug x equals 0 for that one, then 0, 0, 0. And if you plug x equals L, L means that 6 over L negative plus 6 over L, L squared, L cubed become cancel out 6 over L, so which is 0. So that's the property of shape function. And this one, H2, this one, x equals 0, 0. X equals L, 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 then 0. Now, this one, x equals 0, 1, 0, 0, 1. And x equals L, L minus 4, 1 minus 4L cancel out, plus 3, so 1, negative 4 plus 3 equals 0. So you got that. Okay. And likewise, x sub 3, if you plug x equals 3, 0. And if you plug x equals L, then 3 minus 2 is 1. And then derivative of that, x equals 0 is 0, and x equals L, 0. And the last one, x equals 0, 0, x equals L here is 0. And then here, x equals 0, 0, x equal L, then negative 2 plus 3 is going to be 1. So you got that expression. Okay. What does it mean? We make the long story short. If I plot H1 function, then H1 function is that one value is there, like a typical, shape function, but slope at there is going to be 0. So you got the 0 slope, 0 slope. So here at x equal L, the function is 0, but also slope is 0, slope is 0. So you got function looks like this. Right? And this H1, I don't have any description for slope. Slope is whatever slope, I don't know, but you got non-zero slope, as well as you got non-zero slope there too. Right? Totally different kind of, characteristic. And then if you look at H2 is the, associated with the slope. X equal 0 is 0. X equal L is 0. But the slope at 0 is going to be 1. The slope is 1. And here slope is 0. So you got 1 slope and go back to here. And then 0 slope, 0 value. That's H2. And H3, then x equal 0, 0. And slope is also 0. But x equal L, value is going to be 1. Slope is 0. So you got graph looks like this. Okay, 0 slope. And finally, x of 4, 0, 0. But slope is going to be 1 here and 0 here. So you got function like this one. That's the nature of this C1 type of shape function. Right? So in this case, as you typically know that H1 plus H2 plus H3 plus H4, adding all shape function, is it equal to 0? You can check your shape function. Adding up H1 through H4, is that equal to 0? Yes or no? Look at that, not this one, but your note. You see 0? Is it difficult to figure it out? Adding all four polynomial equal 0, they cancel out? Yes or no? No. Like 1. Where is 1? 1 doesn't cancel out. X, where is X? Doesn't cancel out. Right? So that's not equal to 0. Then that is also a little different from the C0 shape function. C0 shape function, add them up together should be equal to 0. Then why this is the case? Right now, our U is H1, U1 plus H2, theta 1 plus H3, U2 plus H4 and theta 2, right? So if you have a beam, U1, theta 1, U2, and theta 2, if you have a beam. So when you talk about this one is, for example, rigid body motion. So beam has rigid body motion, that means this one is going to move, let's say a rigid body translation, move like that one. Right? Then what do you see? When you have a rigid body motion, that means this is going to be 0, this is going to be 0. Right? So we don't have to worry about H2 and H4 because theta itself is going to be 0. Then U1 and U2, this displacement, that displacement equal each other. That means from here, I can see that H1 plus H3 should be equal to 1. right, to represent the rigid body motion. So check yourself. H1 plus H3. Is it equal to 1? Right? So that is equal to 1. Right? So that's also the difference between C0 and C1 shape function. But this one also physically makes sense because it represents a rigid body motion. Okay? Then, once you develop shape function, let's evaluate element matrix. So element matrix, let's say element is from 0 to L, lowercase l. This, right, from the previous formulation. So EI mostly constant. Again, if it's EI is function of X, doesn't matter. You can, this can be function of X. So in Galerkin's technique, W is going to be also equal to shape function H1, H2, H3, H4, and comma XX means that's second derivative. And also U is going to be second derivative multiplied by this one, right? Because U is H1, H2, H3, H4, and U1, theta 1, U2, theta 2. So taking a derivative of that is going to be derivative of that, and because those are going to be the constant at the nodal point. So that is going to be this. So product of that is going to be 4 by 4, assuming this constant for simple case. Then if you evaluate this one, so take a derivative of your shape function, second derivative. Okay, second derivative is straightforward, right? So for example, we took the first derivative. Second derivative is going to be negative 6 over L squared plus 12x over L squared. So if you do that second derivative and evaluate this one term by term, then you come up with this. So this is again lowercase l, dose L. Okay, L squared. So this is element matrix for beam bending. Okay, element matrix for beam bending. So it depends on the element size. Yes,
You said you used the Galerkin's method,
Galerkin's method.
but isn't the definition of the W, the derivative of the trial function over dA?
So the bottom line Galerkin function is we are using same shape function for test and trial function. So we develop H1, H2, H3, H4, for here for our trial function. Then using same H1, H2, H3, 4 is for the test function 1, 2, 3, 4. That's the Galerkin's technique. So again, this is, as you can see, that symmetric matrix. You see this is symmetric matrix. You got the symmetric matrix.
Yeah, you can just replace W with the shape function.
So W is going to be, test function is going to be selected by the shape function in Galerkin's technique. Because we use the same function for trial and test function for Galerkin's technique. Any question? So you evaluate this one for every element and add them up together properly. Again, this is going to be U1, theta 1, U2, theta 2. Then you'll come up with system matrix for element. And especially for this one, this is called element matrix, but in particular element stiffness matrix. Stiffness. Okay. In structure, they use stiffness. Stiffness means how stiff the the structure. So element stiffness matrix. So in this case, element stiffness matrix, of course, proportional to beam rigidity, how rigid the beam EI, as well as the length of the beam. You can see that the length is going to be larger, then matrix become overall value become smaller because you got the L cube in here, right? So longer beam is going to be less stiff, right? Shorter beam is more difficult to deflect. So stiffer makes sense. This is going to be proper also related to the length of the beam, stiffness of the. Any question up to this point? Then what about element vector? This term. W times Q. Again, using Galerkin's technique, repeating same thing. Test function is replaced by shape function. 1, 2, 3, 4 shape function. This one does not have any derivative. So shape function H1, H2, H3, H4. And Q is whatever function we know. You have to carry out integral. But if the Q is going to be constant, if this is going to be constant in one element, you got the constant Q. Right? It's node 1 and node 2, U1 and theta 1, U2 and theta 2. Then if you evaluate this one mathematically, we don't do anything special, but other than just mathematical, integration of that shape function, then you come up with this one. What does it mean? This is the force. So that's going to be 6/12. So the length is L, and this is the Q0. Then 6/12 is 1/2 Q0L. That's the force. And same thing here. 1/2 Q0L. Okay. And then this one, Q0L square over 12. So that's going to be Q0L square over 12. And this is negative. So we define this is positive for the rotation. So negative means this is going to be actually opposite direction. So Q0 L square over 12. So in other words, what I'm saying is that this is the actual applied load in the beam for this element. But as I talk about in chapter 5, in finite element solution technique, everything have to be represented at the nodal point. So in other words, other than a nodal point, I cannot represent this, the load like a flux. We cannot represent that one. So we have to find equivalent flux or equivalent load at the nodal point. That means in here, we got this force and this moment at the nodal point is going to represent this one. Right? So this is the actual problem. That is finite element representation of this node in the formulation. Then do you see any relationship between this and that? This the physically applied load, and finite element I use, instead of that, I represent that using this, concentrated force and moment there. Do you see any kind of correlation between the two. Is that arbitrary? At least if you look at that, the total force Q naught times L, that's the total, right? So half goes here, half goes here, so sum is equal to that one. Correct? Sum is equal to that. Then what about this moment? Why all of a sudden, Q naught L square about 12 and Q naught L square 12 in the opposite direction? So you have that one. Can I ignore that one? Just represent this one by this. Answer is no, because it does not follow your formulation. Okay, so you have to use this quantity. Then what's the meaning of this quantity? There is some physical correlation. What does it mean? If I have beam and then let's say clamp at both ends, okay, let's apply the load opposite direction just to this one, right? If I apply the load opposite direction, then to maintain equilibrium, if you solve this beam bending problem, this is going to be statically indeterminate, right? Because you got extra support. If you solve that one, the reaction force and the reaction moment, right? That is exactly the same as this. Exactly the same as that one. So it's not arbitrary, right? Then if I have a beam, to make it simple, I divide it into same number of elements, right? And then this subject to loading, constant loading, right? Then using this representation, this element as this force and this moment, and next element, this is that, this element, right? And this element, same thing. And this one, same thing. And the last one, also same thing, like that, right? Correct? Now, if you assemble them together in the system H column vector, what do you see? This and that cancel out because they are opposite direction. This is added, correct? But this and that cancel out. And this and that cancel out. This and that cancel out. What's remaining is going to be this and that. So there's no moment in the middle, as you see in here. Only forces, right? Correct? But also, if you see that, this is L squared, this is L. So if you refine the mesh, so element size becomes smaller and smaller and smaller. Element size becomes smaller and smaller and smaller. What do you see? This is going to be much smaller than that, because this is going to be second order, this is the first order. So in other words, this momentum can be ignored eventually. So in other words, that what I'm saying is their representation exactly match with that one when element size becomes smaller and smaller and smaller. Okay, so this is exactly right formulation. Correct? Of course, in this case, element size is not same. So in other words, this element length is a little different from that one. Then this value, because L is different, so they may not cancel out each other, right? But still, that's going to be second order compared to the first of the force, so that when L becomes smaller and smaller, that's gonna be ignored. So that when you define the mesh, those moment effect is going to be ignored. Eventually, you have only the effect of the force. Make sense? So let me stop here. So if you have any further question, then I'll answer for you, and hopefully I can see you the Tuesday. All right?